morning, everyone. Come on in. All right. How are we doing? Questions while we wait? We're a bit early here. Yep, that's exactly what we're going to do. Partial derivatives. We're going to extend the notions of calculus to higher dimensions. So limits, continuity, partial derivatives. I hope to start today. What day is the exam? We're looking at October 21st to 23rd. We're giving a 3-day, I think. We were hoping to make an announcement yesterday to that effect. Somehow it didn't happen. So probably today. So 21st to 23rd is what we're looking at. Well, somehow they decided that those were the days. It's probably only going to be on sequences and series. Well, chapter 11, I should say. So including Taylor series and stuff. No real announcement yet, but it's looking to be 21st to 23rd. No. It's only going to be on chapter 11. Well, again, that's what we're looking at right now. No announcement has been made, so it's still possible that it's going to be later, but it's looking to be next week. No past exams, no. Look, it might be later. It might be later. There's no announcement has been made yet, so yeah, exactly. I don't know. Well, look, today's the 23rd. Today the 13th. If you decide to write it on the 23rd, that is 10 days. So we're good. We're still in that 10-day window. Right? It's gonna be a short exam anyways. It's an hour and a half. So 72-hour window. It's a timed exam. 1.5 hour exam. So you have 3 hours plus a half hour. Morning, everyone. All right. Again, it's my understanding that it's only going to be sequences and series, but be on the lookout for an announcement today, probably an email. I think one of the other profs was going to send an email. I couldn't say about the difficulty. The sound is not good today? Is there an issue with the sound? Is it just Louis Charles, or is it? Uh-oh. Wait, sound is good and crisp. How about now? Yeah, there was, it's raining here today, and I'm in the basement, and there's a sump pump going on and off. So it might have been that. Yeah. Right. So it was a sump pump. You'll hear it going off about every 10 minutes or something. No linear algebra today, unless you've got specific questions. We can address those. Otherwise, we'll start with new material in a minute or two. I suspect the class list will be emailed. I suspect the class list will be emailed. Yeah. You are responsible for all the linear algebra content, right? I mean, we reviewed it for a reason. Namely, we're going to use it. Yep, it's possible that you have questions finding lines and planes on the final. In fact, we'll see very shortly that these questions arise naturally. And if you have a question about series, you can post it as well. Somebody wanted the Maclaurin series for this. Let's kick it up a notch and ask, what is the 101st derivative at 0 of this function? No practice midterms. You should be doing lots of questions from the book, I suspect. Again, I think it's going to be Professor Humphreys writing the exam. So I don't want to venture as to what the questions are going to be, but I suspect they'll be very fair. I don't think there'll be anything you didn't see in the lectures. No update on proofs. I don't know how many questions. Consider this, you know what to do. Right, we're going to find the Maclaurin series. We're going to find the Maclaurin series for this function. We're going to find the Maclaurin series for this function, and that's easily seen to be, you know what that is. Minus 18x times 9x squared to the n. So minus 18, 9 to the n, x to the 2n plus 1. And that's the Maclaurin series for the derivative, so we're going to integrate. And we see that this is equal to minus 18, 9 to the n, x to the 2n plus 2 over 2n plus 2 plus an arbitrary constant. But when x is 0, which is an interval of convergence, of course, right? C is 0. So we see that f of x, or the ln x, ln of 1 minus 9x squared, has Maclaurin series. Minus 18, 9 to the n, x to the 2n plus 2 over 2n. This should have been 2n plus 2. There it is. Thank you. 2n plus 2. I don't expect you to know by heart what ln of 1 plus x is as a Maclaurin series. In this case, this was a terrible choice. Let me change it to the 102nd derivative. I don't know if there are going to be proofs on the midterm. Yeah. Let's wait for the announcement. And again, nobody's written the exam yet. We don't even know who's writing the exam. I'm suggesting Professor Humphreys, so that neither my class nor the other instructor's class have an advantage one over the other, but we'll see. So there it is. This is the Maclaurin series for the ln of 1 minus 9x squared. And if we're looking for this 102nd derivative at 0, we will consider the coefficient of x to the 102. In the Maclaurin series, the coefficient of x to the 102 is 102nd derivative at 0 over 102 factorial. And in here, the coefficient of x to the 102, when is this 102? It's 102 when n is 50. So minus 18, 9 to the 50. This is x to the 102 over 102. And there you have it. The 102nd derivative at 0 is minus 18 times 9 to the 50 times 2 times 101 factorial. David is asking if it's okay to take the 101st derivative of the derivative of the original. Well, fine, but I mean, are you really going to do that? Are you going to differentiate this 101 times? That? Oh, you mean in the? Oh, I see what you mean. I see what you mean. Nice point. Nice point. Yeah, good point. All right. There was actually a series question. Why don't we address that before we continue on? Consider this series. You know what to do, I'm sure. You can easily show that this so claim k ln k over 1 plus k cubed is less than or equal to k to the 3 over 2. I am not doing 264 next semester. It's all good. Whoever is doing it, I'm sure you'll have a pleasant experience. So here's my claim. Well, so how do we make that claim, right? I mean, you know about ln. You know ln, you know the graph of ln x. The graph of ln x goes off to infinity, but it goes to infinity slower than any power of x. So here, if you can show that ln k is less than k to the 1/2, then you're good to go. Right, so in other words, here really what I'm going to show is ln k is less than or equal to k to the 1/2. Yeah, it's the sum problem I was talking about. It'll last for about a minute. It's raining quite heavily, so. Right, let's prove that. By looking at the limit as x goes to infinity of ln x over x to the 1/2. Yeah, Samuel is asking about binomial theorem. That's exactly it. Right, so let's prove this. What is this limit? Well, first of all, this has the form infinity over infinity, so you can use L'Hopital's rule. Derivative of the top, derivative of the bottom. You're dividing by a fraction, so you're going to multiply by the reciprocal. And you get 2 over root x, whose limit is 0. What does that mean? That means that for large values of x, the ln of x over square root of x is going to be very close to 0. So you can make it less than 1. i.e. ln x is less than or equal to root x for large values of x. So for large values of k, ln of k is less than or equal to root k. And there it is. So since this is true, then this is going to be true, and you can show that this converges using the limit comparison. With the series 1 over k to the 3 over 2. So this one is going to converge by using a limit comparison with this one, so the smaller one converges as well. Very good. All right, let's move on. Let's move on. Right? I mean, our point now is, really in the remainder of this course, is to extend the notions of calculus to higher dimensions. So if you think back to Cal 1, what did we start with? We started by considering limits. For large, I mean, let me address that, right? For large values of k, but that's really all you need because you have an infinite sum here. So as long as it's true for the tail end of the series, those last infinitely many, that's all you need. So yeah, so the idea is to extend the notions of calculus to higher dimensions. And in Cal 1, we started with limits, so that's exactly what we're going to do here as well. Now, if you think back to Cal 1, if you are going towards a value A, there are only two ways to go, right? Limit from the left or limit from the right. But if you move to one dimension higher, to the xy plane, and you fix a point AB, well, now there are a lot more ways to go, right? I mean, you can go this way, but you can also go. There are, in fact, infinitely many ways to approach a point AB. So this illustrates the difficulty in going from one dimension to two dimensions. Let's introduce a definition. We say the limit as xy goes to AB of f of xy is L if, well, let's write out the same definition we had in Cal 1. If f of xy can be made arbitrarily close to L by taking xy sufficiently close to AB. Can you assume one to be a constant and evaluate it in a lower dimension? You cannot. Because if you do that, that's assuming you are only evaluating this limit here. If you are taking the y as constant, or these limits here, if you are taking the x as constant. There may be other paths. So of course, you understand exactly, as Juan is suggesting, the only way to consider all paths, right? If you want to prove something for all paths, the only way you're going to be able to do that is with the epsilon-delta definition. So to check all paths going to AB, we need the epsilon-delta definition. I don't know what chapter this is. We'll be doing stuff from page 960 in a moment. So what is the epsilon-delta definition? Let epsilon greater than 0 be given. Well, I mean first let me start again. We say the limit as xy goes to ab of f of xy is L if epsilon greater than 0 is given. There exists a delta greater than 0 such that what? Such that f of x can be made arbitrarily close to L by taking xy sufficiently close to AB, but not equal to AB. I should do that. Should have added that, because as you know, limit is the behavior of the function as you're getting closer and closer to AB, not necessarily reaching it. Such that if xy minus AB is less than delta, then f of xy minus L is less than epsilon. You know the difficulty in playing around with the epsilon-delta definition. You know that this becomes very difficult, and this is even in higher dimensions, so it's even harder than it used to be. But it's a necessary evil because that's the only way you can check all the paths leading to the point AB. However, if you're able to display two paths on which the behavior of the function is different, then you're all done. Let's take a few examples from the book. We are asked to show the limit does not exist. Well, it doesn't matter. It doesn't matter that you haven't seen epsilon delta in Cal 1. You're seeing it now. It's all good. It's not like those who saw it in Cal 1 remember it or enjoyed it. Everybody hates it. Exactly, right. In Cal 1, instead of having the point xy, you just have the point x. And instead of having the point AB, you just have A. So instead of this, it's just x minus A. Instead of the modulus of xy minus AB. Well, Aaron never understood why it was necessary, and let me tell you why it's necessary. This definition here, right, of the behavior, right? All we're saying is that f behaves like L. It's unmathematical. It's unmathematical, and you cannot do anything with it. What does that even mean? The behavior of the function. We need some concrete math to be able to prove things. And so you move to the epsilon-delta definition, a more rigorous, a more difficult setting, but the proofs become easy in that context. Could you use L'Hopital's rule? Well, first of all, we have an issue, namely that now you have, right, because as Tiffany points out, you have a 0 over 0 if you just blindly plug in. But you have a function of several variables now. So what does differentiation mean in that setting? We have not discussed that. Plus, there is no extension of L'Hopital's as we know it. Exactly. All right. So instead, so first of all, I mean, the question gives us a big hint here. The limit does not exist, right? So we are looking at, for the behavior as x goes to the origin, as xy goes to 0, 0. So can we display two paths which behave in different ways? Well, I mean, you can go to the origin on the x-axis, or you can go to the origin on the y-axis. Right, so let's see what happens here. On the x-axis, when y is 0, on the x-axis, when y is 0, what are we looking at? Right, if you restrict your attention, so on the x-axis, right, so you'd be going towards 0 from here. When y is 0, numerator is 0, denominator is x squared. So of course that limit is easily seen to be 0. So if the limit exists, it has to be 0. Right here, the distance between the two is getting smaller and smaller. Exactly that. Right, so on the x-axis, you're finding the limit is 0. On the y-axis, when x is 0, we have 0 over 3y squared, which is also 0. These agree, right? So we have taken two paths and we get the same answer. But I mean, we know the limit does not exist. So maybe taking some other path might be different. Why don't we try on the line y equals x? Of course, you want to take a path that goes through the origin, right? You don't want some function going through the point 0, 0, 2 here, right? You want it to go through the origin. Here we're just doing trial and error. We're hoping to come up with two different paths that do not agree. So x-axis or y-axis, these agree. What about on the line y equals x? If y is equal to x, what do we get? 2x squared on top and x squared plus 3x squared on the bottom. Or you add these, you get 4x squared, the x squares cancel. What is the limit? Limit is easily seen to be 1/2. Well, if the limit did exist by these observations, the limit should be 0. Now we see that taking a different line, a different path to the origin gives you a different answer. So now they don't agree. And now we conclude that the limit does not exist. So to show that the limit does not exist, all you have to do is come up with two different approaches to the point where the behaviors don't agree. Let's try another one. Same question. Here we are told that the limit does not exist. What does the limit y equals 1/2 visually mean? Imagine you were trying to graph this function, right? Back to this one here. Because as you know, limits help you graph. So what we're saying is that on the x-axis, well, in fact, on the x-axis, your function is always 0. On the y-axis, your function is always 0. So here, this function is going to be 0 on the axis. But on the line y equals x, your function is 1/2. So there it is. Then somehow it dips to 0 there and there. I don't know how, but yeah. That's geometrically what's happening. Consider this. Well, when y is 0, so on the x-axis, James is asking, what would it take for the limit to exist? The necessary condition is that the function behaves in the same way on all paths going to the origin here, in this case, right? So if all paths going to the origin, if the function behaves in the same way, then the limit exists. So of course the obvious question is, how do you check for all of them? Epsilon-delta. Well, and we, right? It's the same question. How do you know that all paths have been tested? Of course, you cannot physically test every single path, right? Because if you look at all the lines, you already have infinitely many lines. And then what about parabolas? And what about x cubed? And what about square root of x? And what about sums and products and all of that? You know, it never ends. Epsilon delta does it for you. Can y be any value? Well, I mean, in these cases, you want to go to the origin. So as suggested here, you don't want to waste any time taking a function that doesn't go through the origin. You want to be, you're looking at the behavior near the origin. So, I mean, of course, if y is 1, you're already in trouble. It's not going to go through the origin. We haven't discussed continuity yet. Let's plus it. Let's not go there quite yet. So if y is 0, what's happening? If y is 0, that's gone, and you're left with the limit as x goes to 0 of x squared over x to the 4. Now you know what that limit is immediately, right? What have we done? By doing this, we're bringing everything down one dimension. We already know the limit doesn't exist, so we're just looking for two paths which don't agree. As x goes to 0, right, this is 1 over x squared. Limit is? Limit is? Infinity, thank you. So if the limit, people, why is everybody saying 0? Right, it's limit as x goes to 0 of 1 over x squared. And as x goes to 0, you get a 1 over 0, and you know in the context of limits, a 1 over 0 is some sort of infinity. You just have to determine if it's positive or negative, and it's positive here because of the square. We are approaching 0, exactly that. So if the limit exists, it has to be infinity. All right. What about if x is 0, right, on the y-axis, right? Now here we did the x-axis, and your function is blown up. What about on the y-axis? When x is 0, that's gone, that's gone, that's gone. So it's limit as y goes to 0 of 0 over y squared, which is just 0. There it is. So these don't agree, limit does not exist. Here's the question. Dan is asking how would the function blow up geometrically? Well, you know what that means, right? That means that as you are approaching 0, the function is going off to infinity. So as you are approaching 0 on the x-axis, your function is going off to infinity. So it will look something like this, but only on the x-axis, right? Because on the y-axis, your function is mapped at 0. Right, so function is 0 here, function is 0 here, but here it blows up. 0 over 0 is an indeterminate form, but here you don't have 0. Well, here you have the number 0. Here you have the number 0. So it's the function is always 0. Because remember, this isn't 0, but it's going towards 0. All right. What's after on? No, it's an or. Or prove that the limit, or prove that it does. So show the limit does not exist, or prove that it does. Is it wrong to always write for x, y going to 0, 0 for cases like if y is 0 or it does not matter? Well, I mean, what I'm suggesting is we are restricting our attention to a particular path here, right? The path x equal to 0 or the path y equal to 0. And somebody's asking the good question, how would we know that the limit does exist? Well, at some point, right, after testing enough paths, you start to ask yourself, I mean, you know, if you test enough paths and you're always getting the same answer, you have to ask yourself, are the paths I'm choosing sufficiently different? And if the answer is yes, then perhaps the limit itself does exist. In which case, it would be a good idea to actually prove it. So let's take this example in particular, right? And we are looking for the limit as xy goes to 1, 2. So 1, 2. So let's test. Let's test. Why are we going to 1, 2? Well, that's what the question is asking. Limit as xy goes to 1, 2. So let's test, right? If y is 2, we can go to 1, 2 this way. We can go to 1, 2 that way. And infinitely many other ways, right? So if y is 2, then we are looking at the behavior as x goes to 1, right? From the left or from the right. Of what? Y is 2. So 2x minus 2 over 4x squared minus 4. And you see what's happening, right? Let's factor out the 2 from the numerator. If you factor out 4 from the denominator, still a limit that has the form 0 over 0, but I mean, you know, you have a lot of experience with that. You can cancel the x minus 1s, and as x goes to 1, this, I mean, you're just in the one-dimensional case here. As x goes to 1, this is 1/4. So without doing any work, if the limit exists, it has to be 1/4. Let's try if x is equal to 1. Is this still limit 16? No, 22. 16, we concluded that the limit did not exist because on one path it was 0, and on the other path it went to infinity. Right? Well, let's, as somebody suggested, let's see what happens here, but it's going to be a limit as y goes to 2 of, if x is 1, this is 2 minus y over 4 minus y squared. And we again get a 0 over 0, which you can factor as 2 minus y, 2 plus y. And these cancel out, and you still get a limit of 1/4. And as somebody had pointed out, it's always the same factorization essentially. And if you look back at your original function, xy goes to 1, 2, you could actually let me rewrite it here for completeness, but you could actually factor the denominator as 2x minus y, 2x plus y. Exactly like we did in both cases here. And these cancel out nicely. Can you use the function y equals x plus 1, which does go through, right, when x is 1, y is 2. So that would be yet another path to try. Absolutely. Absolutely. And I was going to try that, but then somebody gave us the answer by suggesting to factor, and we're left with this business, 1 over 2x plus y. And now you're thinking to yourself, well, there's no issue with that function, right? You don't get a 0 over 0 or anything of that sort. You can just plug in, but we don't have yet a theorem that allows us to plug in, right? If you plug in x equals 1, y equals 2, you get 1/4, which agrees with the limits we had before, but that is not sufficient. Both axes, right, is not sufficient to conclude. You would have to test every single path going to the point 1, 2. But it seems rather clear that this limit is going to be 1/4. So let's prove it. How do you know which points to test? Well, I'm going to say trial and error in the beginning, but you have to look at your function. You have to look at your function, and you have to have an idea of how your function works. That's going to be the good answer. So Now the claim is that this limit is equal to 14. Did I say 14? I meant 1 over 4. Let's prove it. What do we need to do? We need to show for epsilon greater than 0 given, there exists a delta greater than 0 such that if xy minus 1, 2 is less than delta, then your function minus the limit is less than epsilon. That's what must be proven. So start with 1 over. Well, first of all, before we start, let's understand what that is. What is that? That's the modulus of x minus 1. That's the modulus of x minus 1, y minus 2. Which is the square root of x minus 1 squared plus y minus 2 squared. Right? That's what this thing is here. It's the distance from xy to the point 1, 2. All right. So start with this. And what is that? Juan Carlos is asking an excellent question. The only issue there is that you're assuming f of x to be a function. So really you're describing paths that are functions. But you could have a path that's not a function. And now if you're making it continuous, that's even more of a condition. So no, it doesn't have to be continuous. It doesn't even have to be a function. So short answer, no. Long answer, probably. You can probably show that if the limit doesn't exist, then you can maybe make a function whose limit doesn't exist, as you're suggesting. I don't know that answer. I'd have to think about that, but I suspect it's sufficient. Let's not resort to that, because again, I don't know that to be true, but I suspect it's sufficient. Putting everything over common denominator seems reasonable. Right? All right. All right. And since it's the absolute value, first of all, I can take absolute value of the numerator, absolute value of the denominator. And I can factor out a -1 because, you've been working with the ratio test. Negatives don't matter. So this is really the same as 2x plus y minus 4. And, maybe I want to group some stuff together. 2x minus 2 plus y minus 2. Why put it over common denominator? Well, it seems like the thing to do. And now, the absolute value of a sum is less than or equal to the sum of the absolute values, right? Also known as the triangle inequality. All right. And this is just 2 times x minus 1. So you see what's happening, right? I've conveniently rubbed it off now, but this thing was x minus 1 squared plus y minus 2 squared. The whole thing square rooted. So you have this x minus 1 and this y minus 2, exactly. Triangle inequality. Says that absolute value of a plus b is less than or equal to absolute value of a plus absolute value of b. So that's what I'm using here. Absolute value of a plus b less than or equal to absolute value of a plus absolute value of b. A very important inequality that we use over and over again. Let me throw in a 2 here for fun. I can do that. I'm just making the whole thing bigger. so that I can factor that out and cancel with the 4, leaving me with a 2. And this absolute value of x minus 1, well, you know what that is, right? That's going to be absolute value, that is the square root of x minus 1 squared. And that is the square root of y minus 2 squared. And I still have a 2 and a 2x plus 1. Right? If I could somehow combine these two, then I'd be good to go. How can I just slap in a 2? It's all good. This inequality allows me to do that. I just figured if I had a 2, then I could cancel with the bottom, and that would be nice. Exactly that. And now you see, if I had this plus y minus 2 squared here, or a plus x minus 1 squared here, that is what is going to allow me to make everything small. Luckily, I can add it to this part, right? I'm adding something positive, so for sure I'm making it larger, and I'm going to do the same for that part. I'm adding something extra, so I'm making everything larger. All right. So what do we have? We have 2 of these. So I can cross that out. Now, can I get rid of this denominator? Right? Because this numerator is going to make everything very small, right? The delta allows me to make it small. If I didn't have the denominator there, I'd be good to go. Unfortunately, it is there, so we need to get rid of it. Here's the question we have to ask ourselves. How large does 1 over this get? Or equivalently, how small does this get? How large does this get? Right? If it's bounded above by some value m, then this whole thing is going to be less than m times that. And this can be made very small, so I'll be good to go. So how large does this get? Or equivalently, if you cross multiply, how small does that get? That's the question we must ask ourselves. how small does this get? Well, I mean, this is what we're looking at. After simplification, we have this. I'm suggesting that the numerator can be made very small by taking delta to be small, right? So if I did not have this denominator, I'd be good to go. Let's get rid of the denominator by asking how large does it get? Right? If this can be made less than m, this whole thing is going to be less than m times the square root, and the square root can be made very small. So I'm going to be able to make this less than epsilon. All I'm saying is, if the denominator wasn't there, we would be good to go. But it is there, so we have to address that. Let's get rid of it. Exactly that. Exactly that. So let's assume for a moment delta to be less than or equal to 1. What does that mean? That means that x minus 1 squared plus y minus 2, if you will. Or in other words, x is between -1 and 1. If you add 1 to both sides, x has to be between 0 and 2. And if you repeat with y, same argument, y minus 2 squared has to be less than or equal to 1, right? Instead of taking this to be gone, you take that one. And so y minus 2 in absolute value is less than 1. So y minus 2 is between 1 and -1. And if you add 2 to both sides, y is between 1 and 3. So from here, if you multiply that by 2, you get 2x is between 0 and 4. And if you add it to this, you get 2x plus y is between 1 and 7. That's nice. So 2x plus y is positive, so you don't need the absolute values. And by restricting your attention to this and cross-multiplying, you get 1 over 2x plus y is less than or equal to 1. Oh, we're buffering? Sorry, I did not realize that. We're back. Excellent. So look, I mean, for those of you who may have missed it, we have this nice inequality for x, nice inequality for y that we got in a similar fashion. Multiply this by 2, and add it to that, we get this inequality. So in other words, 2x plus y is always positive. And if you restrict your attention to the first 2 terms and cross-multiply, you get this. You get that. So this is positive. and it's less than or equal to 1. If you let delta be less than or equal to 1, this is less than delta, right? So it's less than or equal to 1. Square both sides, you get this. Square both sides, you get that. And this is the sum of two terms which are positive. So if you remove 1, you get something smaller. X minus 1. If you remove this 1, you get something smaller. Similarly, if you remove that 1, you would get y minus 2 squared is less than or equal to 1, which is what we had here. So you have both of these. And this implies that x is between 0 and 2. Or that 2x is between 0 and 4. This implies that y is between 1 and 3. So if you add these two things together, you get 2x plus y is between 1 and 7. First of all, 2x plus y is positive now, right? I mean, we've shown that. It's positive, so you don't need the absolute value. And moreover, that is less than 1. So let's finish it up. Turns out the end is 1. If delta is less than 1. So by choosing be the minimum of 1 and epsilon, this is going to be, which is less than delta. Delta is the minimum of these two, so delta is certainly less than or equal to epsilon, and we're done. We set delta less than or equal to 1 because we needed it. We were asking the question, how large does this get? And by choosing delta less than or equal to 1, we see that this doesn't get very large. It was to get an upper bound on this business. Look, I realize that this was not the easiest first question to do. I didn't expect it to be this difficult. Probably should have done it ahead of time. And is actually equal to 1 here. Right, that's what this says. Limits to infinity work as well, absolutely. Maybe we have time for another example. So does the limit exist? In fact, this proves the limit was equal to 1/4. That's what we proved. We proved the limit was equal to 1/4. What does the top mean? let delta be the minimum of 1 and epsilon? Well, it means exactly that. We're going to take whichever one is smaller. Right? You're starting off with an epsilon. You don't know what it is. Some epsilon greater than 0 that is given to you. So if epsilon is smaller than 1, the delta is going to be equal to epsilon. If the epsilon is bigger than 1, you're going to take delta to be 1. Can you explain the part with the delta epsilon here, you mean? Well, it's exactly that, right? I'm saying delta is the smaller of the two. Delta is the smaller of the two. Because you don't know what epsilon is. Epsilon greater than 0 is given to you. Epsilon greater than 0 is given to you. You're going to choose delta to be the smaller of these two numbers, right? Because remember, to get an upper bound on 1 over 2x plus y, we made use of the fact that delta was smaller than or equal to 1. How do you go from the inequality to proving the limit is 1/4? Well, look at the first thing we wrote down. We wrote down the definition of what we needed to show. We must show that blah, blah, blah. And that blah, blah, blah is exactly what we showed. Consider this. So it's the same question. Either show the limit does not exist or prove that it does. So we're going to take a few paths going to the origin and see what happens. Can it be another number in epsilon? Maybe. Maybe. I mean, look, the proof isn't unique. So, yeah. You know, you just have to adjust. It's a terrible example to start off with. And, you know, I mean, so if x is 0, what happens? Right? So first of all, we're going towards the origin. So maybe we're looking at the y-axis when x is 0. Let's see what happens. If x is 0, this is the limit as y goes to 0. When x is 0, this is 0. So it's 0 over y to the 8, which is easily seen to be 0. Maybe let's try the x-axis. So if y is 0, when y is 0, that's 0, but that's also 0. So it's 0 over x squared, which is also 0. So, you know, these agree. Maybe it exists. Does delta less than or equal to 1 always work? Of course, you know there's never an always in math, right? So the answer is no. Juan has hit the nail on the head there a bit too quickly because I wanted us to try a few lines, right? If you try y equals mx, a line through the origin of any slope, right? What happens? This is the limit as x goes to 0 of x times m to the 4 x to the 4 over x squared plus m to the 8 x to the 8. And if you factor out an x squared from the bottom, one plus m to the 8 x to the 6, this cancels out with that one, leaving you with an x cubed. And as x goes to 0, this goes to 0, so denominator goes to 1, numerator goes to 0. So you see that on any line through the origin, the limit is 0. You might want to try parabolas and so on, but Juan has given us the answer. Was it 1? No, actually, Naloy here. Naloy gave us the answer first. I thought it was 1. But Naloy has suggested try y equals x to the 1/4. Right? Which goes like this. Right? When x is 0, y is 0. So this does go through the origin. And why would you even try that? Well, that's, like I said, you have to look at your function and adjust. You're thinking to yourself, if this is x, then the numerator is going to be x squared. And this is going to be x squared. So the denominator is going to be 2x squared. The x squares are going to cancel. And that's what happens. That's why you have to look at your function and think about stuff that's going to cancel out. And in this case, if y is x to the 1/4, this becomes x times x over x squared plus x squared. Or x squared over 2x squared, whose limit is 1/2. And we're done. We have displayed two paths which go on which the function behaves differently. The limit does not exist. How are we doing? Do we want to take a moment just to do a simple example of a limit that does exist that should probably have been done beforehand instead of that long, complicated one? Let's do it. And we'll end with that. Consider this example. Actually, why don't I throw in a plus y here? Is that too easy? Let me change it to, let's do an easy one first and then we'll do that one. Let's do the x. Let's just say x. And then we'll do 3x squared plus xy. On the left, the denominator would be 1. I'm not sure. All right. So, with your experience of limits in Cal 1, you know very well that this limit is going to be 0. So let's prove it. Let's write down what needs to be shown. So we must show that for epsilon greater than 0 given, there exists a delta greater than 0 such that and your function minus 0 is less than epsilon. This is what needs to be proven. But this thing, right here, what does that say? That is, first of all, this minus 0, 0 doesn't play a role here, right? You just get xy. And that, the modulus of xy, is the square root of x squared plus y squared. Right? So it's this square root of x squared plus y squared, which can be made very small. Exactly as Naloy suggests, when you do the epsilon-delta definition, you do assume from this does prove it for every single direction. Right? So it's this which can be made very small. So start with that. Start with what you have, right? I mean, we want to conclude this is less than epsilon. That's our conclusion that we want to come to. But again, the minus 0 doesn't play a role here. It's really just absolute value of x. And as you know, this is the square root of x squared. If only you had a plus y squared here, we'd be good to go. But you can make it. Because if you add something, if you add something positive, you're just making it bigger. And now, this can be made less than delta. But you don't want delta, you want epsilon. So let delta be epsilon. And so this, which is less than delta, is actually less than epsilon. And there you go. Very nice. How are we doing? One last one, one quick one. I claim that this limit is 0. Gabriella, you know there's never an equals. You know there's never an always. Let me throw in a 2 here. Right? What do we have to show? We must show that for epsilon greater than 0 given, there exists delta greater than 0 such that if this is less than delta, then your function minus the limit is less than epsilon. And again, you know that this is really, it's the same as we had here. Right, so this is what is going to allow you to make everything small. All right, so look at your 2xy minus 0. First of all, the minus 0 doesn't play a role. So it's 2xy. Take the 2 outside, 3 steps, but take the absolute value of every part. There it is. Here's my question to you. Which one is larger? Absolute value of x or absolute value of y? Who knows? If the absolute value of x is larger, this is going to be less than or equal to, right? If the absolute value of x is larger, let me replace the absolute of y with the absolute value of x, and you've got something larger. If it was the other way around, if the absolute value of y was larger, then I could have replaced this with that. If I add the two, then for sure, if the absolute value of x is larger, this is going to be less than or equal to just this. So it's true. If instead the absolute value of y is the larger one, then this is less than or equal to that. So since I'm adding them and they're both positive, this is even bigger than each of these separately. And this is just 2x squared plus 2y squared, or 2x squared plus y squared. Now you see that we have this right here. So this is the same as saying if you square both sides, you have this. So what are we going to do? Right? You see what happens? This is really square root of x squared plus y squared all squared. Let's not view it as that. So if I want to make this less than epsilon, right? That's my goal. So as long as delta be the square root of epsilon over root 2, this is less than delta, so less than 2 root epsilon over root 2 all squared, which is equal to epsilon. All right, I think we've had enough. We probably had enough way before this example. But there it is. If you're trying to prove that the limit does not exist, 2 different paths on which the function behaves differently, you're good to go. If, however, you keep getting the same answer, then the limit might exist, and then you have to prove it using the Epsilon-delta definition. How are we doing here? Probably shouldn't be asking that. I know it's difficult. Try your hand at that. We'll pick this up again on Thursday. Thank you all for coming. Expect an email today as far as the midterm is concerned. Well, how many times do you have to check? I don't know. I mean, look back at the other example we had there with the x, y to the 4 over x squared plus y to the 8. If you didn't see what had to be done, if you didn't see the good path to take, you might have expected the limit to exist. Where did the 1 over root 2 come from? Well, it comes from this 2, right? We want to get rid of that 2. I was not planning on doing more epsilon-delta examples, but if you've got questions, we can address them on Thursday. Well, I mean, look, we got up to here, right, with relative ease. And this is the square root squared. And this is what is allowing you to make it small, right? That's your delta. If you replace, here's what you might want to do. If you replace this thing with the delta, and remember that you want to make it less than epsilon, right? So now solve for delta. And there you go. Well, I mean, replace the smaller with equals here. Right, this whole thing is less than 2 delta squared, and you want to make that less equal to epsilon. And now it's just a question of a little bit of algebra to solve for delta. That gives you the delta you wanted. Practice this. The book has lots and lots of exercises. And we can discuss that again on Thursday if you've got questions. Otherwise, we'll move on. Thank you all for coming. I'll see you then.